Hi, in this video I'll talk about the bias variance decomposition. I'll briefly remind you that we're in the supervised learning setting where we consider an unknown target function f from x to y. Our goal is to approximate f by some hypothesis h. And to do this we have data d of the form x1, y1 all the way through x capital N, y capital N. Here each xi is in our input data space x, and each yi is equal to f of xi, which is in y. So you can think of this as yi would then be f of x1, and y capital N would be f of x capital N. So you can think of this data sample as a lot of samples of points in the input data space and the value of x on these points. So we have a lot of examples where we know how f behaves, and we want to use all these examples to approximate f. To be a bit more concise and clear and formal of what we mean by approximate, we'll define an error measure. So this error measure will actually define two error measures: the in-sample error rate and the outer-sample error rate. So the idea is, if h has low error, then it approximates f well. And it'll be clear in a moment why we have two different types of error. So let's start with the in-sample error rate. So the in-sample error rate will be the sum of I is 1 to capital N. So we'll sum over all the points in our dataset, I is 1, I is 2, all the way up to I is n, capital N. And then we'll see what is h on xi. And how much does it deviate from yi? So remember that yi is f of xi. So this is essentially how much does h deviate from f on the ith point. This is what this says. So we'll have this deviation squared, and we'll have 1 over capital N. This will be our in-sample error rate. So it's essentially how much does h deviate from f in the data sample. So the problem with the in-sample error rate is, if you just memorize all these points, and you would be able to get in-sample error rate 0. So this would be kind of cheating. So what we really want is, we want to perform good on points we didn't see before. And this is what the outer sample error rate captures. So the outer sample error rate will be h of x minus f of x, similarly to before. So it'll be the deviation between h and f. And again, we'll square this deviation. But we want to rid the dependency on the dataset. We don't want you to be able to depend on the dataset in any way. So what we will do is, in this supervised learning setting, we have an assumption that there's some underlying probability distribution these data points follow. So we'll take the expectation with regards to this probability distribution. And in this way, we'll rid the dependency of the specific dataset. So we'll take the expectation with regards to x, and then we'll look at the expected deviation of h and f. So we have two different error measures here. We have the in-sample error measure and the outer sample. This is something we can compute. This is something we can make an algorithm that attempts to minimize. This is what our learning algorithms typically do. But we really care about the outer sample error rate. So in this video, we'll see how we can take this outer sample error rate, which we care about, and decompose the outer sample error rate into the bias of our hypothesis and the variance of our hypothesis. Before I show you how to decompose the outer sample error rate into bias and variance, I want to talk a bit about bias and variance first. So you can think about bias as how much we expect to deviate from the target. So how much do we expect to deviate from the target? And you can think of the variance as how much we expect to deviate from mean, or expectation. How much do we expect to deviate from the mean? So you can think of this in a nice way if you think of it as like playing darts. So let's say we have 4 dartboards, and then we'll consider 4 different cases In the middle we have the target, and the target will be the bullseye. So imagine I throw in these boards with low variance, and imagine I throw in these boards with high variance. And imagine over here on these two boards I have low bias, and on these boards I have a high bias. Then if I have low variance, well, then I expect to deviate a little from the mean. So the throws will be pretty close to each other. They won't vary a lot. And the bias will also be low, so I'll expect to deviate little from the target, which is this guy. So probably I'll expect the darts to land something like this. Now, if I had a high variance, then this would change because I would expect to deviate more from the mean. So the darts would maybe be something like this. I would expect each of the darts to deviate a lot from the mean of the darts. So if I had high variance, I would expect to deviate from the target. So I might have a low variance, and they might not deviate a lot from each other, but I would deviate a lot from the target, so maybe they would all land over here. Now, if I have high bias and high variance, I could expect to see something like this. I would expect all of them to deviate a lot from the target, which is in here, right? This is my target. My target is the bullseye, but I would also expect them to deviate a lot from the mean. So this is a nice visualization of how bias and variance are different types of things you don't want in your hypothesis.